The problem below shows a cross-section of a sphere and a conducting shell around the sphere. There's a shell, and inside is a sphere. Now the radius of the inner sphere is 2 centimeters. But the shell has an inner radius of 4 centimeters and an outer radius of 5 centimeters. Now there's a charge on the inner sphere of 18 microcoulombs, so it's positively charged. And any conductor is going to have its charge spread out. The excess charge is going to spread out on the surface of the conductor. So let's draw the positive 18 microcoulombs being on the outer edge of the inner sphere. We also find that our shell has a total net charge of -7 microcoulombs. So I can write that the net is -7. But it's a little more difficult to figure out where that -7 is going to be distributed for the outer shell. For the inner sphere, it's easier to figure out where the charge will reside, because we know that inside any conductor that's in electrostatic equilibrium, the field inside will be 0. And according to Gauss's law, if the field inside is 0, then there isn't any net charge inside the object. However, it's more difficult to figure out where the charge will be distributed on the outer shell. The principle that the field inside is 0 still holds, though. So for the outer shell, we can have a Q on the outside surface, and we can have a Q on the inside surface, and they don't have to necessarily match. But here's one thing we will always find with this type of setup. If we have a certain amount of charge on the sphere, call it Q of the sphere, we'll always find that the Q of the sphere is the same size as the Q on the inside shell. So we'll find that the positive 18 microcoulombs on this sphere will actually attract 18 microcoulombs of negative charge on the shell's inner surface. So the Q of the inside of the shell will equal the opposite of the Q of the sphere. This information will allow us to find out how much charge is on the outside of the shell, because we'll always have the relationship that the net charge on the shell will be the sum of the inside charge plus the outside charge. We know that the net on the shell is -7 microcoulombs. We've determined that the inside charge is -18 microcoulombs. So we can now solve for the charge on the outside of the shell. There must be 11 microcoulombs of charge on the outside of the shell. We need to make sure that our work checks, that the negatives on the inside of the shell plus the positives on the outside of the shell do add to a -7 net. That looks like it checks. Now that we understand the problem, we're asked to find the electric field at 4 different distances from center. One of them is right here. There's a point which is between the space of the shell and the sphere. There's one which is in the shell's material itself, 4.5 centimeters, and then finally there's one outside the entire setup. So the electric field at R equals 1 centimeter is easy to answer. It's inside the sphere's metal. Its net charge will migrate to the outside. What we could do is create a Gaussian sphere of radius 1 and show that the net charge inside is 0. If we do the calculation for Gauss's law, and divide by our area, we'll see that the charge enclosed is 0. That makes the electric field 0 at that point. But what about this point, which is 0.03 meters from center? Well, we can create a Gaussian sphere. We know that we have plus 18 microcoulombs inside that Gaussian sphere. So we can use that information to calculate the field at that point. I'm going to use the area of that Gaussian sphere. It's 1.8 times 10 to the 8 newtons per coulomb. Notice that the field at this point does not depend on the shell that's around it. The shell around it actually can't contribute anything to the field at that point. What direction would the field be? It would be outward. It would point from positive to negative. So we will see electric field lines in the gap between the shell and the sphere. It'll create a capacitor. Now we want to know what is the field. 0.045 meters from center. It's going to be 0. But just to prove that it really will be 0, let's use Gauss's law. Create a cylindrical shell which cuts right through the metal itself. And we said that there would be plus 18 microcoulombs on the sphere inside and negative 18 microcoulombs on the inside of the shell. That means our enclosed charge will actually be a net of 0. So, the electric flux is 0, and therefore the field must be 0. Now we can find the electric field outside this whole setup at a radius of 6 centimeters. Okay, for that one, we can create a new Gaussian shell. So this one is at r equals 1 centimeter. This is at r equals 3 centimeters. And this one's at r of 4.5 centimeters. Let's do one last calculation at r of 6 centimeters. To get the charge enclosed, we could add all the different charges that we had found. That's one way to do it. Okay, so now let's find the field by dividing the area. So we're going to get 11 microcoulombs on top over 4 times pi times 0.06 squared times 8.85 e to the negative 12. And I get 2.7. 2.7 times 10 to the 7 newtons per coulomb. And one last interesting thing to look at here is we see that the field outside the object is really due to the charge that resides on the exterior surface of that object. And if we take a look at the original charges that were on the objects, we had a positive 18 microcoulombs on the inner sphere, and a total of negative 7 microcoulombs on the outer object. If we combine those together, we get positive 11 microcoulombs. And so we see that the net charge in this system will migrate to the exterior surface of the system. And that net charge on the exterior is what's responsible for creating the field at points outside the system. We could even evaluate the field using Coulomb's law for fields and a net charge of 11 microcoulombs, and we should get the same answer as we did above. So regardless of what's happening inside this spherical capacitor, the 11 microcoulombs on the surface is what really matters when it comes to finding the electric field at this point.